Okay, so here we're going to start talking about solving some of these higher order differential equations. Well, we're going to start trying to solve them. So the idea of this section is to say, well, what if we knew one of the solutions to these higher order differential equations? Could that then lead us to another solution to the differential equation? Right? So we're not completely solving these from scratch yet. But what we're going to do is we're going to start solving them assuming we already know one solution. Okay, so that's this concept of reduction of order. And we're going to do it by using the first solution to help us reduce the second order differential equation to a first order differential equation, hence reduction of order, reduce the order from a second to a first. All right, anyway. So again, what did I say we were going to do? If we have a known solution to a second order differential equation, one interesting thing that occurs is that these types of equations, we can use its solution to construct a second solution, which I already said. So let's suppose y sub 1 is a known solution to the second order homogeneous differential equation. And we already talked about second order, homogeneous, linear, and why this equation right here is all those things. Okay? So let's just suppose, though, that we already know one of the solutions. How would we know that? Well, that's something we're going to eventually have to learn, how to find the first solution. Well, let's just assume we know that one. Okay? We're also going to assume that a sub 2 of x is not equal to 0. The reason why that is because if this first thing right here is equal to 0, then this wouldn't be a second order differential equation. It would really only be a first, because that would zero out that whole term. And if it's just a first order, then we don't need any of this. So we're going to assume that this is a second order, okay? And so what we want to do is we want to find this second solution, y sub 2, and we're going to do it using this reduction of order process, okay? And basically the idea is we're going to use a substitution, okay? We're going to use a substitution to help us get there. Okay, so we're going to suppose that y1 is a non-trivial solution to that previous differential equation. Now, non-trivial solution is basically saying that y equals 0 is not what we're looking for. Y equals 0 is a solution to really any homogeneous linear differential equation. So if you think about it, like a2 y double prime plus a1 y prime plus a0 y equals 0. That's a second order linear homogeneous differential equation. And this will solve that regardless of what a2, a1, or a0 are. Because what the derivative of 0 would be 0, the second derivative of 0 would be 0. And so if I plug that in here, here, and here, of course, this side would equal 0, and therefore that would solve the equation. But we consider that to be the trivial solution, because that's going to solve every homogeneous linear differential equation. So we're going to ignore that. We're going to say we're looking at a non-trivial solution, so not one of those. Right. So then what we're also looking for is to find that second solution, right? We want to seek the second solution such that y1 and y2 are linearly independent. And we've talked about this. We want our solutions to be linearly independent. We're not concerned with a bunch of solutions that are linearly dependent, because they would basically be considered the same solution. They're just multiples of each other. Okay? So we want linearly independent solutions. Well, if y1 and y2 are linearly independent, then that means that the quotient of y2 and y1, if I divide those two functions, is going to be a non-constant. Okay? Now remember, linear dependence, right? c1y1 plus c2y2 equals 0. As long as c1 and c2 are not both 0, right? This would be linear dependence. Okay? y1 and y2 will be linearly dependent if this were to occur. I could also rewrite that as, let's say, c1 y1 equals negative c2 y2. I could also divide this to here and divide this to here, so I could say negative c1 c2, c1 over c2 equals y2 over y1. Again, this is if they're linearly dependent. So you see, if I was to divide these two functions, it would be equal to this constant. Okay, that's if they're linearly dependent. But if it's not equal to a constant, if the quotient is a non-constant, then that tells me that this was not equal to 0, and therefore these are linearly independent functions. Okay, so if when I divide y1 and y2 and I get something that's non-constant, then I should get a function of x. Well, because this is a function of x, this is a function of x, so then it should be equal to a function of x, non-constant. Well, if y2 over y1 equals this u of x function, okay, I can multiply y1 to the other side, and I can say y2 of x equals u of x times y1 of x. And this is u, not mu, like when we were doing the integrating factor. All it's doing is holding place value for something, though, this function of x. Okay? So take a closer look at this. What this is telling us is that this second solution that we're trying to find should be equal to the first solution, which we're saying we would already know, times this random u function of x that we would need to come up with. So the way we're basically going to come up with this u of x is by substituting. And we're going to substitute this second solution's form into the original differential equation and see what happens. And this is going to be a trick we're going to use a lot this semester, where we're going to make some assumption about what a solution should look like. And so we made this assumption that this is what the second solution should look like, okay? Well, if it is in fact a solution to the differential equation, then when I plug this in to the differential equation, it should satisfy it. It should work, okay? And we're going to use that trick a lot in this semester. We're going to somehow come with a educated guess as to what the solution should look like, and we're going to say, well, let's see what happens when we plug it in. And when we plug it in a differential equation, certain things are going to happen, and that'll dictate when, in fact, that educated guess will solve the differential equation. So that's what's going to happen here. So we're going to do that, and we're going to find out what u of x would have to be. And once we figure out what u of x would have to be, we have our second solution, u of x times the first solution. Again, we're assuming we know this first solution, which is somewhat faulty in our argument. The trick would be then, how do we find that first solution? We'll get there eventually. Okay, so here's the process we're going to go through. First, we're going to put this second order differential equation in standard form. Okay? In order to put it in standard form, just like with the first orders, we got to make this leading coefficient here become a 1. So we have to divide everything through by a sub 2 of x. Okay? And in which case, this would be divided by a sub 2, this would be divided by a sub 2, and then so we'll take this quotient function here, this rational function, and we'll call it p of x. We'll take this rational function here, and we'll call it q of x. Okay? And so this is our standard form for a second order linear. Somewhat similar to our first order, but now we have p of x and q of x. P of x is the coefficient in front of the y prime. Q of x is the coefficient in front of the y. All right. So first thing we're going to do is put in standard form. That's something you're going to have to remember because that's going to be key in this process. So p of x and q of x have to be continuous, though, right? We can't be dealing with any parts of the differential equation that are not continuous. And since they're rational functions, we got to worry about that. But anyway, let's suppose we know this first function, y sub 1, okay? And we know that our second solution that we're looking for, okay, which we're just going to call y, okay, for right now. Let's assume that this second solution that we're looking for is in the form of u times y1. Well, if that's what the solution is going to look like, then when I plug it into this standard form differential equation, it should satisfy it. So that means I should take the derivative of this function. So that means y prime should be u y1 prime plus y1 u prime. Now all I did was use the product rule here. I'm taking the of x's off of everything because it's just easier to write. But product rule, right? Take the derivative of u times y1 plus y1's derivative times u. Okay? So that's all this is. This is product rule. And then if I take the second derivative and I combine any common terms, I would get this is my second derivative. Okay? So I plug the first derivative and second derivative in here and here. And what I'm going to get is, if I simplify this, I'm going to get u times this plus y1 u double prime plus 2y1 p y1 u prime. All right. And this would just be by plugging in and grouping like terms. I would get to this point. The reason why I do it this way is, if you notice here, okay, this should be equal to 0. Why? Why should it be equal to 0? Because y1 is a solution. So when I plug y1 in here, here, and here, it should satisfy the differential equation, which means it should make it equal to 0. So this is the original differential equation with y1 plugged in and should be equal to 0. Well, if that's equal to 0, this whole thing is gone. Okay, oops, I went too far. This whole thing here is gone. So now all I have is this piece. All right, so let's take a look at this. So if I look a little bit closer at this piece here, this y1 u double prime 2 y1 plus p y, this should be 1. There should be a little 1 right here. Okay, u prime. We can make a quick substitution on this thing. Now, the substitution we're going to make is that w equals u prime. And this is where the reduction of order comes into play. So if we make this substitution, if w equals u prime, then w prime equals u double prime, in which case u double prime goes to, u double prime goes to w prime, and u prime goes to w. So now we're looking at a first order differential equation instead of a second order differential equation, in which case we could try and figure out how to separate this because it's actually separable. So if we separate this, we can get the w's and the y's separately from each other. Again, this should have a little y1 on it. Okay, make sure I keep that the whole time. And we go to separate this, which is going to be the way we're going to try and solve this. Now, ultimately, remember, what are we trying to find? We're trying to figure out what this function u equals. Okay? Well, I just got rid of the u's. There's no u's in this anymore. Well, we'll have to get back to u. What we could do is we could figure out what w equals. And once we figure out what w equals, that could lead us to figure out what u equals. All right, so let's separate. Okay, so again, we're going to separate. So we're going to take this w and bring it over here with this w prime, or take this y, bring it over here. Again, I keep having to fill in this little y1 right here. Okay, so if we have w prime over w, which is the same thing as saying dw over w, it's w prime over w. And then when I divide by the y1, well, what's going to happen here? This is being divided by y1, and this is being divided by y1. So if I separated that, I would have this piece, okay? And I would have just p dx over here, because the y1s would cancel. And remember, everything's a function of x. I dropped off that of x, so if we're looking at this thing here, everything's a function of x. So if we integrated these, right, what would happen? If we integrate this, we're going to get this log of w. If we integrate this one, it's another logarithm because it's a prime over itself, so that's going to be 2 log of y1. And then if I bring this to the other side, okay, and integrate it, Well, this is going to make it negative, but you're going to have the integral of p dx plus some c value. Now, we don't know what p is. Remember, p is just this random function of x from the beginning. What we can do here is we can figure out what w equals by just slowly isolating things to get w by itself. Well, I could bring these two logs together here. Okay, I'll bring the 2 in, so it's a square, then put the two logs together, so it's a product. Then I can get rid of this log by exponentiating both sides. So here, if I pull this out, if I had e to the negative integral of p dx plus c, okay, basically take this whole thing and put it up in the exponent of an e, and I do that so that this side I can cancel that e in the log, giving me just this piece. What I would get is, since this is added up in the exponent, I could write it as e to the negative integral of p of x dx times e to the c. But e to the c is technically just a constant in itself, so that's where you have this, if you see c1 e to the negative integral p dx. So I'm going to call this e to the c c1. Okay. You can call it c. I'm going to call it specifically c1 because we're going to get another c to show up eventually anyway when we build our whole solution. So once I get to that point, if I divide by y1 squared, okay, I then get what w equals. So here's what w equals. But remember, w equals u prime. So if w equals u prime, this is what u prime equals. Well, then what I want to do is I want to actually really figure out what u equals, remember. Well, if I know what u prime equals, then if I integrate u prime, I should figure out what u equals. So u should be the integral of this whole thing that we just found with respect to x. And there you go. So then, what do we want? We don't really want that. We want to know what the second solution is, right? But the second solution should be u times y1. So if I then take this and I multiply it by y1, there goes your second solution. So now we have this second solution to our differential equation based off of the first solution. Now look at all the pieces that are here to build this second solution. First piece, y1. Again, we're going to say we assume we know that. The only other thing we need to build this second solution is p of x. C1 is a random constant, e is the natural exponential. The only other thing in this whole thing that we need besides that first solution, which again, we're assuming we'll know, is p of x. And where does p of x come from? It comes from the original solution, the original differential equation, put in standard form, and looking at the function that's in front of the y prime, right? That's your p of x. We didn't say p of x had to be a specific kind of function. All we said is that p of x has to be continuous. But p of x is that function in front of the y prime in the original differential equation when we put it in standard form. And when we do that, we could find this second solution. Now this second solution, you can think of this right here as a formula for the second solution. I'm not too big on formulas and memorizing formulas per se. I usually like the process better. But when it comes down to this and how we're going to use this, the formula is the fastest way to get through this process of finding a second solution. We'll go through and I'll show you an example where we kind of do this whole process of making the substitution and then finding w, then therefore finding u. But you're going to find real quick that if we could just remember this formula, it's going to save us a heck of a lot of time to find the second solution. And in the next section, when we go to say, all right, this is all well and good, but it assumes something that we probably wouldn't ever know, which is the first solution. And we go ahead and try and find the first solution and then try and use this formula. You're going to see the formula is going to be the best way to go. Okay? Okay, so we'll look at this first one. And I'll do it both ways. We'll do it with the formula and we'll do it the formal way that we really just looked at when we talked about the solutions just being, y1 and y. So first off, they gave us one of the solutions, e to the x, and they're saying e to the x is the solution to this differential equation. Notice that this is a homogeneous differential equation. That's what we're working with here. And it's real quick to see that that actually does solve the differential equation. So the derivative of y1 would just be e to the x again. And so if I plugged y prime in here, or sorry, second derivative, which would also be e to the x, I plug that in here, and I plug the original function in here, clearly when I subtract them, I'll get 0. So you see real quick that e to the x is definitely a solution to this whole thing. All right, so now we have that one solution. Now we want to find a second solution. So we're going to do it two ways. First, I'll do it the long way. Again, this is not the way we're primarily going to use it, but it'll help make sense of what we just looked at. So then we're going to say that y2 should equal u times e to the x, u times y1. All right? So then y2 prime should be u times e to the x plus u prime times e to the x. And again, it's product rule. I'm doing derivative of e to the x, which is e to the x, times u. Then u prime, derivative of u, times e to the x. And then u2 double prime should be u e to the x plus u prime e to the x plus u prime e to the x plus u double prime e to the x. Again, remember, product rule, product rule. So this is the product rule for the first piece. This is the product rule for the second piece. All right. Notice there's two of these in here, so I'm going to call that 2u prime. It's driving me nuts. 2u prime e to the x. Okay? So what I'm going to do is I'm going to take this and I'm going to plug it into the differential equation. If this is what the solution should look like, then it should satisfy this equation. So y double prime is again u e to the x plus 2u prime e to the x plus u double prime e to the x. I have no idea what's going on tonight. Let's see if we can get through this. All right. Minus y, which is u e to the x, equals 0. And that's, again, just plugging it right in here, plugging y and y double prime into the differential equation. Notice these two cancel each other out, which is that thing we talked about where the first solution should give you, all the pieces should give you 0. So that's all the pieces that have the u in them. That was one thing we looked at. Okay. Then what we have is this remaining piece, which we're going to then make our substitution. And we're going to say w equals u prime. So w prime equals u double prime. And so we're going to get w prime e to the x, that's this piece, plus 2 e to the x times w. And that equals 0. So then we're going to separate. I'm going to get w prime over w. And I'm going to get divide by e to the x. So I'm going to get 2 equals 0. Bring this over to the other side. So then I have w prime over w equals 2, negative 2. I'm going to integrate both sides since now it's separated. Integrate this side. I'm going to get the log of w. Integrate the other side with respect to x. Remember, everything's a function of x. And get minus 2x. Okay. I could do the plus c here. I could put the plus c in later. Doesn't really matter. I'll put the plus c in here for now. So then what we're going to do is exponentiate both sides. So e on this side, e on this side. That's going to give me w equals e to the minus 2x plus c. The plus c here, I could actually bring out to the front because I could write this as e to the 2x, e to the minus 2x times e to the c. Remember, adding in the exponent, multiplying the bases. This is just a constant. So finally, I could say w equals c e to the minus 2x. Now remember, that's w. We want to know what u equals. And then we want to plug it in here to get our solution. So if this is what u prime equals, then u should equal the integral of this, which should then be minus 1/2 c e to the minus 2x. I could also then say plus c again, but again, we'll see how that would develop. We'll just leave it here. That's your u. We technically could take this minus 1/2 and embed it inside the c. I don't have to. I can. But let's just take it and plug it into here now. So what we're going to have to do is multiply it by an e to the x. So therefore, our second solution should be minus 1/2 c e to the minus 2x times e to the x. Simplifying, saying this whole thing is just our constant, we would get minus 1/2 e to the minus x. So technically, or c e to the minus 1/2. So everything but the constant part, that's really our second solution, e to the minus x. Now why I say all this constant stuff doesn't matter. All this constant stuff doesn't matter because remember what we're going to do ultimately, this is what we talked about in the intro stuff, was that once we find two functions that are linearly independent, in this case we just found one to be e to the x and the other to be e to the minus x, we're going to combine them with a linear combination to write the general solution as y equals c1y1 plus c2y2. So we're going to put these c's in there anyway. So like this c here I could have actually ignored because all that did was come out as this plus c, and I can embed this minus 1/2 into the c, and ultimately I could just ignore it and say, well, really the second solution is e to the minus x, because I'm just going to build it back together anyway. I'm going to write this as c1 e to the x plus c2 e to the minus x. And you can check to see whether or not e to the minus x actually solves this differential equation by taking the first and second derivative, plugging it in. You see it's going to end up giving you 0 when I plug it in for y double prime and y. But so a lot of this constant stuff we can forget about because we're just going to build it into our general solution anyway. But if you had it in there, it's not wrong. So if I wrote this here instead of c2 e to the minus x, if I actually wrote, say, minus 1/2 c2 e to the minus x instead of just c2 e to the minus x, it's fine. But I'm just embedding more and more into this constant. All right, so that's the long way to do it. Then there's the shortcut. Shortcut is to use the formula. So if we get rid of some of this here, right, let's clean this up. In order to use the formula, the original differential equation has to be in standard form. And so you want the leading coefficient to be a 1, in which case we already have that. Then you want to find p of x. So in this y double prime, we could write this plus 0 y prime minus y equals 0. The p of x is in front of the y prime. So in this case, p of x is 0. Right? So it's in standard form. We're missing a y prime, but that means that the coefficient in front of y prime is 0. So then think about the formula. y2 equals y1 times the integral of c e to the negative integral of p of x dx over y1 squared dx. Now, this constant here, much like I was talking about this constant over here, technically can come outside the integral because it's a constant multiple, and can come all the way out to the front here, in which case I really don't need it because I can just introduce it later when I'd say my general solution would be c2 times y2. So what I'm going to start doing is I'm going to start dropping that c off the formula. And we'll put it back in later. and you see we're going to end up with the same e to the minus x. So y1 was e to the x. The integral of e to the negative integral of p of x, which was 0 dx. Let's see if I can get this to work. Dx over y2 squared, which was e to the x squared dx, would be how we would have to come up with our second solution. Again, e to the x being the first solution, p of x being 0. So what do we get here? And this is starting to look sloppy. What do we get? We get e to the x times the integral of e to the negative integral of 0 dx. Well, integral of 0 is just a constant. So this is e to the negative c over e to the x squared dx. Now remember, e to the c, e to the negative c, that's just a big constant. So I could just call this whole thing c, and I could pull it all the way out to the front. Okay? Remember, I dropped off this other c too, which would have combined with all this stuff. So, let me erase some more. So if I take this, I have e to the x times the integral of 1 over e to the 2x dx, because e to the x squared is e to the 2x. Now, in order to integrate that, I'm going to bring it up as e to the minus 2x dx. And you see right away that we end up with the same answer as e to the x times negative 1/2 e to the minus 2x. Multiply this in here, which is the same thing we did down here, and you end up with this minus 1/2 e to the minus x. And there's your second solution, which is what this whole thing started with, right? This is y2. Again, we could take the minus 1/2 and all these c's we brought out, lump it all together, and we'll just call that c2, but really the second solution is this function, e to the minus x. So we saw both ways to do it. Again, I'm not big on memorizing and using formulas. I kind of like the process better in most cases. But in this case, the formula is the way to go. And that's really how we're going to use it moving forward anyway. So I really want you to get comfortable with that second solution formula. So again, the second solution formula is the first solution times the integral of e to the negative integral of p of x dx over the first solution squared dx. I'm dropping all that constant business out of this thing now. All right, so remember, it hinges on two things. The first solution, which is right here, that's y1, and p of x. Now, p of x has to come from this being in standard form. Notice there's no y prime again. Now, it's not in standard form because I got an x squared here, but still, if I rewrote this as x squared y double prime plus 0 times y prime minus 6y equals 0, and I divide everything through by x squared, here and here, this is still going to be 0 over x squared, which is still going to be 0. So p of x in this case is still 0 again, and y1 is x cubed. So I go to find my second solution, and what's going to happen? X cubed, x cubed times the integral of e to the negative integral of 0 dx over x cubed squared dx. So a lot of the same stuff. X cubed times the integral of e to the 0 is a constant. This here will be e to the negative c, which is just going to be one big constant, over x to the 6 dx. This constant can come all the way out. So I have x cubed. I really have x to the minus 6 dx. Integral of x to the minus 6 is going to be what? Add 1, divide by, so minus 5 over minus 5. So x to the third x to the negative 5 all over minus 5. But again, this constant, negative 1/5, will come out with where that c was, so we're only focused on the function, which will be x to the minus 2. So x to the negative 2 is the second solution. And then if I wanted to form my general solution, the question didn't ask me to do that, just to find the second solution. But really, ultimately, this is what we want to do. We would say C1 times the first solution plus C2 times the second solution. And however much constant you wanted to embed inside that C2, you can. Remember, this C came out, we kind of ignored it. This negative 1/5 that we're divided by also came out, we kind of ignored it. All that's embedded inside the C2. And the only thing that would change would be if we did an initial value problem, what you would determine C2 to be may look a little different, but ultimately the whole general solution would still be the same. So we try and keep it as simple as possible. So you see how much faster the formula really is for calculating the second solution. So we're just going to continue using it. Again, we want to make sure we're put into standard form. We have our first solution. This is not in standard form. I have to divide the x squared through this whole equation, and then that would turn the p of x from negative 3x, which it really isn't, to actually negative 3x over x squared, or negative 3 over x. So my second solution is going to be my first solution times the integral of e to the negative integral of p of x, which is negative 3 over x dx, over, again, the first solution squared. So here our p of x isn't 0, so we're going to do a little bit more work here. This negative can come out with that. It turns into a plus. Integral of 3 over x is going to be a log. So we get x squared times the integral of e to the 3 log x over x to the 4th. Now, in order to simplify the e and the log, we know we've done this before, but remember, you got to bring the 3 in first as a power, then cancel. So what do we end up with? This would be x squared times the integral of x cubed over x to the 4th dx, which would then give us x squared times the integral of 1 over x dx if we simplified, which would then give us x times ln of x. And notice I just dropped off all plus c's anywhere. I mean, technically, when we do this definite integral, we should have a plus c, which eventually will just dump itself out. It'll be e to the c, and it'll dump itself out to the front. Then when I do this definite integral here, I should have another plus c, but I ignore that, because again, I'm just going to keep adding these in later. So anyway, the second solution is x ln of x. Now, the question didn't ask us to do this, but let's just do it anyway. The general solution should be y equals c1 x squared, first solution, plus c2 x ln x, which is the second solution. All right, so, sorry, x squared. I don't know why I lost that square when I went from here to here. This is an x squared, so x squared ln x. That looks better. Okay. Let's do one more. Okay, this one looks a little bit worse, but still, same deal. Here's your first solution. P of x, again, divide by x squared. Gotta put in standard form. So your P of x is going to be 1 over x again, because again, I take this and divide it by this. So my second solution would be my first solution times the integral of e to the negative integral of P of x over the first solution, squared. Looks pretty rough, but take it one integral at a time. So here, this one is going to be your log. Okay. So we're going to get sine x over square root of x times the integral of e to the negative log over, this will be sine squared over x, because if I square both of those, that's what's going to happen. Here I'm going to cancel, but before I cancel, bring the negative 1 in. So I'm going to have e to the log will cancel, and this will be x to the negative 1. So sine x over square root of x times the integral of x to the negative 1 over sine squared x over x. Now what I have is a fraction, because it's really 1 over x divided by a fraction. I flip and multiply. The x's are going to cancel. So now I get sine x over square root of x. It's still just sitting here the whole time. It's outside the integral. Really, I have to deal with this integral, which is really going to turn into 1 over sine squared x dx. So then as long as I can integrate 1 over sine squared dx, then I'm done. Well, it's not that hard to do if you know your basic integrals, because I'm going to write this as cosecant squared x dx. And then I just have to do the integral of cosecant squared, which you should all know. So we all know that this should be minus cotangent x. So we get sine x over the square root of x times negative cotangent x. But cotangent we could write as cosine over sine, so we could do a little bit better here. So sine x over square root of x times cosine x over sine x. We could then cancel the sines and finally get our second solution to be cosine x over square root of x. So there's your second solution. That's y2. Once we have our second solution, our first solution, we could then say the general solution is c1y1 plus c2y2, and come up with that by filling in y1 and y2. So again, the formula basis of coming up with the second solution for these, I feel, is just your best bet. It's more simple process than the way we came up with the formula. And again, what we're going to use this for is going to be using the formula. So I think we're better off doing it that way.